Okay, thanks Dr. Yao for the nice introduction. So, I know the talk today is still very important because Dr. Yao still retained the application token last night, right? So I still worked very hard to get it. Okay, so currently lead a group called as Learning and Vision in NUS. So this group was founded in early 2008. So currently we mostly keep about maybe 20 to 30 members, and the research directions and topics are quite diverse. So including the multimedia, computer vision, and machine learning. Yeah, but actually multimedia is the main focus. Yeah. So for today, this is ICD, so I will mainly introduce the research work related with biometric. But biometric, actually in the past few years, the topics have been changed to the hard biometrics, including both soft and hard biometrics. Yeah, so basically for me, I'm interested in the face and the body, the human body. Yeah, so based on for the face, I'm interested in how old is this person and what is the gender, and but more importantly, I'm interested in how we can change a lady or male to be more attractive. Yeah. And at the same time, we are also interested in what the person will look like after about maybe a few years, maybe 10 years or 20 years. Yeah, so you can find the application, for example, for cross-age face recognition. Of course, another very important topic is what is the identity of the person. But recently, I'm pushing a relatively new direction as a human parsing. So means I expect to understand the whole details of the body, including the hair, the clothes, the back, and other things on the body. Yeah, we expect to have very precise parsing. So means piecewise parsing on the whole body, and then you can do a lot of things. So for example, important application will be the person identification. But actually, if you can have the human parsing information, you can have many other e-commerce opportunities. Yeah. So my original plan actually is to introduce the low part, so means for face recognition and the human parsing. But our organizers mentioned that maybe even more people will be interested in how you can change a lady to be more attractive. So today, actually the topic will be quite diverse. So not just constrained to be the deep learning, we also introduce some biometrics not related with the deep learning part. Yeah. So for the first part, we are mainly focused on how you can do aging and how you can do the aging for the mainly for ladies or for ladies. Yeah. So for the aging, actually is more complete. So actually, I will focus on how to make a person to be more beautiful and more attractive. Yeah. So this is a system we developed in 2013. We call this as Beauty Experts. And basically, we expect to simulate how a girl or lady will do their makeover. Makeover means including the makeup and the hairstyle. So if you carefully check, you will notice that for a girl, so first she will select the foundation and then apply on the face. And the next step, actually, will select the lip gloss and then apply it around the lip. And then we'll select this kind of eyeshadow template, so means the style and the color, and then apply around the eye. And finally, we'll select the hairstyle and do the hair make the hair. So to simulate this process, actually we build a system, two functions. First one is to recommend what kind of cosmetic items and what kind of hairstyle should be applied for the lady. And secondary, so means we use computer vision technology to synthesize the effect of this cosmetic item, and then to simulate on the face, you can visualize what the person, the lady, will look like after all these different cosmetic items. Yeah. So we build up a the flow chart of the systems like this. First, we collect enough number of this kind of data from the website. These photos actually favored by a lot of people. A lot of people feel I like these photos. Yeah, and this will be the positive samples to beautify a lady. And then we need to learn a recommendation model. Then when you have a photo which, for example, without this kind of makeover, then if you say, I want to please recommend some makeup and the hairstyle, then the system will call the recommendation module, and then this kind of cosmetic items will return to the user. Then you say, I want to try, and then the system will call the synthesis module, then the visual effect will be synthesized on the face of the girl, and if you like, then you can purchase. Yeah. So this is a whole e-commerce cycle for the whole framework. But the most important component will be the recommendation module. Yeah, so here, definitely, first we need to extract some of these kind of visual features, and then we will express these makeup cosmetic items as the beauty attributes. But notice that the direct from the visual feature to this kind of beauty attributes, actually the modeling will be very difficult. So we define for some of these kind of beauty-related attributes. This actually will implicitly infer what kind of beauty attributes should be utilized for the girl. So basically, for the beauty attributes, we define the attributes for the hair, for the eyeshadow, the shape, eyeshadow color, and the foundation, and the lip gloss. In total, we have 9 different types of beauty attributes, and all these beauty attributes, we are defining what kind of cosmetic items you should utilize for the synthesis process. Also, as I mentioned, we define about 21 kinds of beauty-related attributes. For example, the face shape, the lip thickness, and the ocular distance, and the race. These attributes will not be changed during the makeover process. So it means before you utilize the cosmetic items and art, this will be fixed. So you can use this as latent variable to infer this kind of beauty attributes. Of course, you need to define some of this kind of low-level or mid-level features, and this will be the representation of the face. So the recommendation model actually is quite simple here, although we have even more complicated model. But the simplest model is to utilize the generative model. It means we try to understand what is the relationship between the low-level feature, the visual feature, the beauty-related attributes, and the beauty attributes. Yeah, we use the GIFs distribution to model the distribution of these favored photos. And then to define the energy function for these 3 parts, we automatically learn this kind of sugar graph to construct the relationship between the different types of attributes. If the 2 attributes are strongly correlated, then we group together as a sugar vertex, and then use the non-spanning tree to find out the relationship between different types of this kind of sugar vertex. And then we use this sugar graph to define the energy function for the GIFs distribution. Yeah. So after you get this one, then it's quite easy. So when you have a new image, yeah, so you first extract the visual feature, and then utilize the beauty-related attributes as a latent variable. You can infer the corresponding beauty attributes. So after you get the beauty attributes, then based on the hairstyle attributes, you can find the most suitable this kind of hair template, and then align the template with the face. You can also align the eyeshadow template with the corresponding individual face, and also you can extract out the face area, the lip area, and then you can do this kind of upper branding to integrate the original face and the hair and the different cosmetic items, and then finally you can get this one. So for example, this is a test image. Yeah. So first you will apply the foundation of the face based on the facial analysis, and then the lip gloss will be applied on the lip area, and then the eyeshadow will be applied on the eye, and the hairstyle will be applied on the hair. Yeah. So finally, you can have this kind of visual effect on how these recommended cosmetic items and hairstyle will look like on your face. And if you like, then you can do this kind of, you can purchase and do this kind of makeup by yourself. Yeah. Okay, so this is a real system. Yeah, so we built up at the end of 2013. So basically, this is the input. This is the input image. This is the image after the makeup, and this is image actually with both the makeup and the hairstyle. And this is the first one is for the Eastern person, and the second one is for Western person. Yeah. So actually, we have a live demo, but today I did not set up here. So if you are interested, for example, visit Singapore, we can show the demo to you. We are also trying to implement this on the iPhone, so maybe after some time you can get an app and you can try by yourself. Yeah. So the next one, the app watch is a video based, it's not image based anymore. So it means you can actually really change the position and the expression of the face, and you can see this kind of visual effect by yourself. Yeah. Okay, so this is the work for the make a person to be more attractive. So another application for this application is that nowadays a lot of ladies will apply the makeup. So it means if you have two faces, one with makeup and another without makeup, actually you can synthesize this kind of makeup by the analysis of the image with the makeup, and then you can do this kind of face recognition, robust face recognition with makeup. Yeah, so this is the potential application. And the second one is the first one is try to make you younger, right? But next one actually I want to make you even older. So it means what you will look like after a few years. Yeah. So the main target is to make this kind of aging process to be personalized, because we can see some of these kind of works which can actually already some works, especially the work in last year from Professor actually that was to synthesize the visual effect, the aging effect, but actually it's not personalized. So it means for different person, the aging process is the same. Yeah, so this actually will not be good for age face recognition. So here we have the basic assumption that one face will be divided into two parts. So one part is the aging component, aging layer. The second one will be the personalized layer. So personalized layer, for example, will express the lower or other this kind of components on the face which will not be changed during the aging process. Yeah. But another one is the aging pattern, aging layer, so means this one will be changed during the aging process. Yeah. So different person will have different this kind of aging patterns. Yeah. So we learn a dictionary, so which include a set of this kind of aging pattern. Each aging pattern will express a particular this kind of aging process. But for each person, their aging process will be the linear combination of different aging patterns. Yeah. So for example, for one age, you can extract out the aging layer and the personalized layer. So the personalized layer will be copied to certain age group, but this kind of aging layer will be the linear combination of the templates for certain age group, and then this reconstruction coefficient will be transferred to another age group. Then you can have a new aging layer, but the same personalized layer. So you combine, you can get corresponding aging face for this person. So it means because two factors. So it means aging. So it means personalized layer will make this aging process personalized, and also this aging layer will have different reconstruction coefficient for different person. So the aging process will be personalized. So we implement two versions to learn this dictionary and how to infer this personalized layer. So one is based on both were based on the assumption that it is very difficult for you to get the faces at the different age groups for the same person. But it's very easy for you to get the faces of the same person in two neighboring age groups. So basically, we learn the dictionary, and but the reconstruction coefficient will be shared in two neighboring age group, and the personalized layer will be the same for the same person. Yeah. So this is one way. So the learning process is quite easy because this is convex optimization problem, but it is not so good for the testing process. Yeah. Sorry. So we also have another bi-level, this kind of aging dictionary learning process. This is based on the assumption that the reconstruction coefficient and the personalized layer will be inferred from the low age group, and then this one will be directly applied for the younger phase and the older phase, and then this one, the optimization problem is non-convex, but for testing it's quite easy. We just get the phase and then get coefficient, then transfer to the senior age. Yeah. So this figure shows how, based on the model, how a younger phase will be changed to an older phase step by step. Yeah. For example, the first one is from 5 to 17, and the second one is from the 14 to 17. Yeah. So these are more results. So basically, we divide the ages into 9 groups, and the first one is the input, and the consequent phases actually are synthesized phase based on the proposed method. So currently, maybe it's still not so perfect, but actually, if you compare with other methods, you can see that this method has some of the advantages. For example, we compare with two systems. One is from the website, is a phase transformer. So this one actually is very interesting. So if you have time, you can try by yourself. Actually, the result is not so bad. But the same thing that this will not give you a personalized aging process. Another one is from Professor C's group. This is the illumination aware aging process. For the same thing, this one will not have the capability to produce personalized aging process. So if you compare the different results, you can see that, for example, for this one, so this input phase, this is ground truth from 32 to 69. So you can see that this one can produce personalized aging process that the bear has been changed from the dark color to the white color. Yeah. But if you use other methods, this effect cannot be actually factory produced. And for this one is, you can see that the shape is more similar to the ground truth. And these two, you can see that if you use the method from Professor C's group, although actually very attractive, very useful, but this one will have the same aging process. But for the proposed methods for different phases will produce different aging process. For example, this one is too slow for the method from Professor IAAP illumination aware aging process, but for this one is too fast. But for the proposed method, because aging process will be personalized, means you can have different aging process for different persons. But this is not the key. The key is whether this kind of aging process can have the cross-age face recognition. Yeah, so we did the experiments on the FGNet because this one has very large age gap, and we utilized a system built up by my own group with the 99.70 accuracy of the labeled face in the white. So if we just directly use the face from FGNet, the equal error rate for the original pairs will be actually quite high. It's nearly, it's more than 14%. But if we, for example, if we have a pair, so this is the younger face, this is the senior face. So if you use the automatic aging synthesis process, you can transfer the age from 11 to the same age group with 32. And then you can use these two phases for the cross-age face recognition. So we have two ways. So one way is we use the ground truth age for the synthesis. Another one, you can utilize actually to use the face recognition, the age estimation to estimate the age for this face, and then use this face as ground truth to synthesize the aging result for this image. So you can see that this is the first one is ground truth. The second one use the estimated age. You can see that the equal error rate can be reduced from about 14 to 8.5. So the reduce actually is quite is significant And also you may notice that if you use the estimate age for this kind of aging process synthesis, the performance is better. That means the second one is better. So because this system is personalized and the result from Professor Six's group is not personalized, you can see that the reduced error amount actually is smaller compared with the proposed new method. Yeah. But anyway, from this you can see that if you can do this kind of aging synthesis well, you can really you can improve the cross-age face recognition performance. Yeah. So nowadays for the social media, you already have many of these kind of images with very big age margin. Right? For example, for the Facebook, it is already there for more than 14 years, right? So actually you will have a lot of faces with the age gap less than 14. Yeah, so the cross-age face recognition is becoming more and more important. Yeah, okay, so this is a purification and aging process. So now I formally move to the deep learning for the biometric. So in the past about 3 years, my group in Singapore was trying to build up an ecosystem for deep learning. So we expect to build up a deep learning platform by ourselves. Yeah. So we expect this system will support the multi-GPU on multi-PCs. That means we can use more than 4 GPU, more than 80 GPU. We can utilize, for example, 100 GPUs for the training. And then, actually for the ImageNet computation, right? So maybe in 2013, if you want to train a model, you need to wait about 10 days to get the model. This is quite time consuming. And second, we expect that this kind of platform can be linear speed up if proper this kind of model is utilized. Yeah. So finally, we built up a platform called as QLink, and this one can help you to implement the deep learning on multiple PC, multiple GPUs. And for example, current version can help you to train a deep learning model, for example, from BookNet, from Google, within 12 hours. Use about 16 hours. Use about 12 GPUs. Yeah. So this actually is impossible in the past few years. But now for just normal researchers, academic researchers, you can, if you have enough GPU, then you can use this platform to train the model very fast. Yeah. So this is a platform to support actually the new algorithm design. So my group, we focus on two parts. So for the deep learning network, we expect this can be more like the human brain, but the learning process will be more like a baby. Yeah. The baby means what? Baby learning is not like what we are doing right now. So nowadays, actually, we are giving us all the training data, so we learn the model. But actually, for baby, it's not like this. You just need to give a very few positive samples. Then the baby has the ability to learn by interacting with the real world. For example, if you want the baby to learn the horse, then the baby just needs maybe just based on 2 images from the children book, and then we have initial model in the brain. She will go to, for example, the zoo. When she saw for example, the horse, she will very carefully observe the horse, yes, then accumulate a lot of these kind of new samples, and then can self-learn and improve the models in the brain. And then next time, for example, on the road in some country, you see the horse, and then to other countries, you still see the horse. So maybe after 2 or 3 years, she can have a very mature this kind of model on the horse with the brain. So in the future, she does not need to learn observe the new horse anymore. Just say, oh, this is horse, and then start to self-learning. Yeah. So means the baby has the capability to learn with very few training samples. Yeah. So my group actually has put quite a lot of efforts to implement this kind of computational baby learning, and even you have a very not so bad model, I still expect that this kind of computational baby learning can further improve the performance by using the unlabeled videos. Yeah. So after you have these kind of new models, then you can apply blind for different applications. So one is for vision, another is for non-vision. For vision, we focus on two parts. The first part is the object, so means environment object, for example, the laptop and the desk and the ship and these kind of things. Yeah. So basically, we participate, as Dr. Yao mentioned, we participate the two competitions, the ImageNet and the Pascal C. We already got, I think, should be around first prize or second prize in these two competitions. Yeah. And for the Pascal C, the classification, so our current performance is still the best in the world. But the second one is not just the general objects. We are interested in this kind of products from, for example, from the Amazon or from China, for example, the Taobao, and we can, for example, in the physical world or some magazine, you see a process or some other products, we'll capture photo, and then you can get corresponding product from the Taobao or Amazon. So we license the technology to Alibaba. So currently, the software called as Snap and Buy is already on the Taobao mobile, so you can try by yourself. Actually, the daily use number is already quite huge. Yeah. And the third part is we expect to understand the user. So this is what I just mentioned. I'm interested in the face and the human body, so means the human parsing. So, but another part is that it's not just for the visual part. You can actually use the deep learning for many other applications. For example, you can do the assistive driving, and you can also do this kind of resource planning. You can also do intelligent recommendation, to the customer, including the service or some advertisements. Yeah. So this is so up to, for example, already have some success application, then you can get more funding, get more funding from industry or from academia, so you can build even larger this kind of platform, then you can progress even faster. This is a so-called ecosystem for deep learning, to survive, for the whole lab. But today we are mainly focused on the human part, so means including the face and the human body. So the face part, because time limitation, only use one word, is how to utilize the new model called as network to learn a model for face replication. So network is motivated by the fact that for the human, the neuron is very complex. So currently, if you want to use the inner product of the convolution followed by the nonlinear response to simulate the function of the neuron, is not enough. So intuition is that you can use more complicated structure to simulate the function of the neuron. So maybe the simplest way is that you can utilize, for example, multi-layer perception. Or actually, this is a general platform. For example, you can utilize Google actually finally utilized the inception module and basically the batch normalization. And even you can, for example, use, for each feature map, you can do the square or p-norm or the square root of the features, and then you can simulate this kind of capability of the kernel, and but you can still use this kind of convolution neural network process to implement the new idea. So means anyway, so we expect that this kind of inner product of convolution can be more complicated. So this is the basic idea. The second one is that currently the convolution neural network, besides convolution layer, we also have the fully connected layer. But this one will make the semantic meaning of the convolution process unclear, because the fully connected layer can change any deformation or transformation into the original signal. So it means actually this will make the convolution layer unclear. So we change the whole network in this way. So it means you can use any other complex this kind of structure to simulate the function of the complex cell. We do not have this fully connected layer, but we only have this kind of average fully. Then the last layer, number of feature maps will be equal to the number of classes. And then for each map, actually the meaning is that for each class, the confidence for different position. So it means the semantic meaning becomes very clear. Very clear. And at that time, we tried, and the performance was the best compared with the models, for example, the max out proposed at later 2013. This work was published in 2014, in the ICLR conference. The underlying reason is that if you use more complicated this kind of structure, this where we can have better local abstraction. So for example, if you use inner product followed by the non-linear response, so maybe, for example, if you want to abstract the concept for example, the ear, and then if you use the simple version, so you can only have the abstraction of the year 1, year 2, year 3, year 4. But if you use this more complicated structure, then you only have the single abstraction, that is the ear. That's why actually the more complicated local structure will be useful. Secondly, as I mentioned, because you do not have this kind of fully connected layer, then the number of parameters will be much smaller. Then you can very easily, for example, a very small model. In future, maybe you can utilize this kind of small model on, for example, smartphones or other smart devices. So this is very important. So basically, a lot of these kind of parameters can be saved. Currently, you can have model maybe just about 1/16 of the original model if you use fully connected layer. So also this is a template. So means you can, based on this template, to develop different types of new algorithm. So as you may notice that QuickNet in the presentation of last year, 2014, they call their QuickNet as deeper network in network. It means first it's deeper. The network actually, they utilize a complicated structure called as reception module to replace the original this kind of convolution followed by nonlinear response. Okay, so we use this actually deeper network in network, and based on the database from Professor Stanley's group released before, so it's about 400,000 images or about 10,000 subjects. Then you use deeper network in network, train the model, and then extract the feature as representation of the image, and then you can train any other this kind of dynamic classifiers. Then the performance can come to 99.7. But you can see that actually from Facebook, CO Hong Kong, and Face++, current results is quite near to this one, but actually still a little low. The performance from Baidu in China, original performance is 99.62, but later they use even more data, the performance actually reached 99.82. So means, but anyway, you can see the potential of the network, deeper network in network, and you can imagine in future if you can, based on other motivations, for example, if you want to reach the location invariant, scale invariant, or other invariants, then you can design different types of this kind of local complex cell or complex small network, and then you can improve the performance. So this is an example based on the current system. So the photos are from one of my friends in Tencent in China. She's the HR of the Tencent. One day she released 2 images on the website. Even her son cannot identify these are from the same person. So every time when she passes by the border officer will actually bring a lot of troubles to her because it's quite difficult to identify these are from the same person. But actually, if you input these 2 images into our current system, our system will say yes, right? Because the computed distance is only 8, but the threshold is 200. So it means the system is very confident that these 2 images are from the same person. So this is for the face, but actually I'm not a real expert in face part. Also my boss Stanley is expert in this direction. For me, I'm more interested in the object recognition, but recently I feel maybe another cue will be very important. So means because in a lot of application scenarios you cannot see the face clearly. The face is too small, or maybe the pose is not so good, or maybe, for example, the lighting is not so good. But the closeness is there. So if you, for example, can do the human parsing properly, for example, you can pass the image into the different human body atoms. So here, for example, we define the 17 atoms including the height, the hair, the face, the upper body clothes, lower body clothes, the leg, the pants, and the bag, and the belt, and these shoes, and these different atoms. So if you can correctly and precisely identify the pixel-wise annotation for these atoms, then you can imagine a lot of cues can be utilized. Not just like before, you give a bounding box on the human body and then you extract different types of features for the human ID. Because you can precisely pass the body, then you can extract, for example, the real closest part. For example, your hand will be here, will be here. Then the hand will not affect the closest feature part. Yeah. So if you can decompose a human photo into the semantic body atoms and have the pixel level semantic labeling, then you can imagine a lot of different applications. The one, for example, is the closest search, right? And also you can utilize the media management. You can also, for example, the first part, you can better do the hairstyle and the makeup recommendation. But more importantly, I think this can be utilized for the VID. Because currently you have the HD camera for for a lot of this kind of surveillance scenario. So it is possible for you to segment or pass the body where. In this area, we cannot say it's very hot area. I think maybe one reason is that it's not so easy to get enough data for the training. And so actually in the past few years, maybe you can only see the works from less than maybe 10 groups in the world. So one group is from Professor Bergs. So she actually is a pioneer in this direction. So, but basically, most previous work is based on the hand design pipeline. So means first you will get this kind of segments. So based on different methods, segmentation, axis generalization, and many other, for example, other methods. And then you will extract the features from handgraphic features from the segments, and then you will use some parametric model or the non-parametric model, give the labels for each segment. And then you will do the post-processing, for example, CRF or some other model to refine the final results. But this actually, if you separate into different components, then the performance for each component will be very important. Sometimes this component can work well, or sometimes cannot. So you cannot guarantee very good performance, although you can see some of the results. So we worked on this direction for quite a few years, I think more than 2.5 years. So we also started from this kind of handgraphic feature and the segment based. Today I will introduce two recent work on this direction. So these two recent work already brought the possibility of the human parsing quite near to the industry application. So the first work is motivated by active shape model. So means we expect to use the star model to explain the human parsing. That is, we consider each atom as a point at the base of our base alignment, right? And then we model two parts. One is the normalized mask of different atoms. Second, we model deformation for different atoms. And then we use two new networks. So one will predict what the mass should be. The second one will to predict the deformation, the distance to the center, and the scale, and the visibility of different atoms. So the normalized atom mass is based on the assumption that for different atoms, also they may be different for different person, but actually they still share some of this kind of shape similarity. So it is possible for you to have settle this kind of templates, and then for a particular person, the mask can be the linear combination of these different templates. So this is the assumption. And then we learn two networks. The first network is called as active template network. So this will actually give you the linear reconstruction coefficient to build up, to reconstruct the mask for a particular person, but the size is normalized. And the second one is called as active shape mask. So this will predict the atom position, the scale, and the visibility of the atom. After you get this, and then you can actually get the confidence map for different atoms, and also for the background. Then combine and followed by the shift pixel smoothing, they can get the result. Yeah, so this is a pipeline for the first try. So to learn the template for different atoms, so we use the non-negative matrix factorization. Also, we tried some other method, but it shows that this one is the best. So we learn 50 templates for each atom. So since we have 17 human atoms, it means actually the 50 by 17 means we have a prediction of 850. So means we will from the input image of the human, and the output will be